Okay, hello everyone and welcome back to this video. And as you must be aware, I have been recording a series of videos related with electromechanical conversion system. And one very important aspect when you are designing or specifying an electric machine is the efficiency. Because the efficiency is basically related with the total power output and the total input power. So the magnetic materials, they have a strong effect on the whole efficiency of the electrical machine, and that is because the electrical power losses. So today I have this very interesting exercise, a numerical example related to the very important active power losses in magnetic material. So without further delay, let me start the explanation of this example. In this example, we consider a very specific body, and in this case is a toroidal core of a rectangular section of 10 millimeter by 20 millimeter. As you can see over here, we have the dimensions of this rectangular section. And in this case, we know also that the toroidal core has a diameter of 80 millimeters. And it's fabricated of a very interesting and very peculiar ferromagnetic material. This material received the name Deltamax. And Deltamax is a combination that is 50% nickel and 50% iron. But more important than that is that the BH curve, the BH loop of the Deltamax material is very peculiar. If you look over here in this figure Q1, the BH characteristic is quite rectangular. So in this case, we decide to use this material because in this case, it will be extremely simple for my students and of course all the audience to calculate the energy in loss density for hysteresis. So as you can see here, there is a maximum value over here, Bm 1.4. As you can see over here, this is the magnetic strength, and you can see that +7 and -7 amp per meter, they are defined in this rectangular section. However, there are three very interesting questions over here. You can see the first one is to estimate the hysteresis energy loss density. And as you can see over here, we are using the letters WH, and H is a lower letter. And this is the hysteresis energy loss density per cycle of the material. Also, question B is estimate the hysteresis energy loss per cycle, and in this case is in the total core. And as you can see now, we are using WH. In this case, H is a capital letter because now we want to obtain the joules per cycle. And finally, we want to obtain the total hysteresis power loss. And as you can see over here, we are obtaining this as PH, where H is capital letter, so at a frequency of 400 Hertz. And as you can see, this total hysteresis losses is defined in watts. So without further delay, let's start this solution, okay? So the first thing that you need to understand is that this very peculiar material that is 50% nickel and 50% iron that received the name Deltamax. As you can see over here, the hysteresis loop is almost defined by a rectangular section. So as you can see in yellow, I use yellow color here to define the area that is defined by this BH curve. And in this case, you can see that 1.5 is basically the retentivity of this material. And also you can see that around 7 here, you can see the coercivity that is basically the magnetic strength. So the first question here is that we want to know the total the total energy that is dissipated when we are using this very specific material. So when we are using this Deltamax, we can use the yellow area over there in order to calculate the basic hysteresis loss density. And using very basic geometric properties, you can see that from here to here, we have 2 Bmax, and from here to here, we have 2 Hc. So what I am telling you is that the total area covered in yellow color here is basically twice the base by the height. And in this case, 2 multiplied by 2, that is 4 bms Hs. So what we need to do now is substitute the numerical values. In this case, Bm is 1.4 Teslas, and Hs is basically 7.0 ampere meter. So when we put inside the equation, we have 4 multiplied by 1.4 multiplied by 7. So as the very end, we have here the result that is basically 39.2 Tesla amps per meter. However, if you prefer to use if you want to use the MKS system and substituting the definition of Teslas and amps, well, you will realize that at the very end, this area over here in yellow color, the units are joule per cubic meter. So at the very end, the total energy loss density per cycle is 39.2 joules per cubic meter. In other words, every time that we are applying the AC signal, one loop across this yellow area is producing a loss of 39.2 amps per Teslas per meter, or in other words, joules per cubic meter. It's very simple for my students. All my students, they can see. If you look over here, let me show you the deduction in order that you remind the concept of the different units. As I said before, the unit for the magnetic flux density is Tesla, and Tesla in the MKS system is basically kilograms over amps per square second. But on the other hand, the magnetic field strength, H, is basically in the MKS system is amp per meter. So when we are covering the BH curve, we are multiplying Teslas per amp over meter. So substituting this definition over here, substituting kilograms over amps over a square second, and substituting the units, you can see here amps with amps cancel, and at the very end we obtain kilograms over meters per square second. So the definition of a joule is basically kilogram per square meter over second square. So basically what I am demonstrating over here is that when we multiply Teslas by ampere meter, at the very end, the unit, as you can see over here, is kilograms meters per second, and that is basically the definition of joule per cubic meter. So what is important that you see over here, is that the BH curve, the area that is covered inside the BH curve, represent the hysteresis energy loss density per cycle. What I'm telling you is that basically the yellow area that we calculate represent the energy dissipation over one cycle on the whole BH curve. However, this shouldn't be confused with the power loss per cycle. That is basically multiplying the frequency by the hysteresis loss density per cycle that we calculate in the previous section. So when we are calculating the power loss per cycle, well, we are obtaining watts per cubic meter. And in this case, the term power loss density in watt per meters and the term energy loss joule per square meter should not be confused. We need to identify that when we are using the term density is basically because we are talking about energy or power that is referred to kilograms or cubic meters. For instance, in question B, we have been asked about the total energy required to circle the core around the hysteresis loop. And to be honest, we can obtain the total joules by simply multiplying the joules per cubic meter by the total volume inside this magnetic core. So multiplying the energy density that we calculate before by the total volume in cubic meters, that will give you the joules per cycle that we are looking for. However, the main complication over here, and to be honest, is not a complication because my students, they have a very good understanding about geometry, is calculating the volume of the magnetic core. And in this core, the geometry is very simple because it's a rectangular cross-section toroid. As you can see over here, I have the 3D representation. You can see the diameter of this magnetic core. And here we have a cross-section. This is the cross-section of the magnetic core. And as you can see, it's a rectangular cross-section. And the rectangular cross-section has a very simple area that is the product between D1 and D2. So now what we need to do is basically calculating the total volume of this core. And to do so, what we need to do is use the basic principle of geometry. And in this case, the core volume will be 2 pi multiplied by the radius and multiplied by the area of the cross section. And the first part, that is the radius of the torus, is very simple because we know the diameter. And dividing by 2 the diameter, we can obtain the radius. However, in order to keep simple or the units, we are using the MKA system. So we are converting those 80 millimeters into meters. So as you can see over here, the total radius is 0.04 meters. Regarding the rectangular cross-section, as I already said, the equation is very simple. It's the product between D1 and D2. And in this case, we are converting from millimeters to meter, D1 and also D2. And when we put inside the equation is the product between 0.01 and 0.02. So as a consequence, you can see that the cross-section area of the rectangular section in this toroid is 0.002 square meter. Finally, it's just an exercise of substitution in order to calculate the volume of the torus, because it will be 2 pi multiplied by the radius that we already calculated here, and multiply by the area of the cross section. In this case, this is meter square. So we obtain over here the volume of the toroid, and in this case, this is in cubic meters. So it's very simple now to calculate the total energy per cycle, loss energy per cycle, multiplying the energy density that we calculate before, joules per cubic meter, 39.2, and multiplying by the volume that we already calculate of the total material. So the answer is over here, after the substitution, 1.97 millijoules per cycle. So it's very simple. At the very end, the total energy loss here for hysteresis per cycle, WH, in this case capital H, is basically the core volume that we calculate and the loop area that we obtained in the previous question, 39.2. So here we have the very valuable, the very important answer, the total hysteresis energy loss per cycle. The final step is that we has been asked to calculate the total hysteresis power loss. And to calculate the total hysteresis power loss, what we need to do is basically multiply the energy, the hysteresis energy loss per cycle that we calculate over here, multiplied by the frequency of the AC signal that we are applying. So in this case, for 400 hertz, and hertz means cycles per second, we multiply the 1.97 millijoules per cycle by 400 cycles. Cycles cancel with cycles, and at the end is the product between 1.97 exponent minus 3 multiplied by 400, and we obtain here finally the total hysteresis power losses, and in this case you can see that is 0.788 watt. So this is a very small losses, but those losses in watts, they represent the power that is dissipated in the whole core. And this dissipation, you must remember, that is related with heat. So in any magnetic core, when we have a hysteresis, these currents moving inside the transformer, they will create eddy currents and also hysteresis losses. And that will negatively affect the total efficiency of the electrical machine. Finally, just a curiosity over here, Deltamax is a very interesting material, ferromagnetic material, and is basically an alloy that is oriented and is 50% nickel and 50% iron. And this material is quite used for high-frequency magnetic amplifiers, where the relative permeability can go as high as 100,000. So this is the end here for this very interesting video. I hope you enjoy, and I will see you very soon with the coming videos related with this topic on electromechanical conversion devices, and of course we will see you in the next video with more practical example. Thank you very much for watching, and I will see you at the next one. Bye now.